What is up, guys? In this video we are going to be discussing the rate law and reaction order, and this is one of my favorite topics in chemical engineering because it is where we really begin to appreciate all the nuances that go on behind the scenes in our everyday lives. And when we look at industry, one of the biggest things we care about is making product as efficiently as possible. And so this is where we begin to see a lot more chemistry in chemical engineering, with kineticists and chemists coming to us telling us that when they change the concentration of one particular species of our reactant, the rate of reaction changed to this degree. And so this is where we really begin to formalize these relationships in math. And so I think it's very exciting stuff that I hope you guys will find interesting as I do. And at a high level, before we jump too deep into the math, think of the rate law, or the rate of reaction, as essentially a rate constant times some function of concentrations of your reactants. And the rate constant, it is a function of temperature. It can depend on the temperature. So for some chemical reactions, having higher temperatures will make the rate constant even bigger, so you're going to get an even faster reaction, but that's not always the case. And then, for other reactions, they're not really going to care about what the concentration is of one of your reactants. And so that's what we're going to discuss when we talk about reaction order. And so to begin with here in this video, what we're going to get when we begin to formalize what these words mean is we generally will denote minus RA to be the rate of consumption of a limiting reagent A in your reaction. And this is going to be equivalent to Ka, the reaction rate constant for species A in your process, and then times, and in the equation that I have above in green, we'll have Ca raised to some alpha power times Cb raised to some beta power. And so a very important thing that sometimes you will be told, and you need to be told explicitly, is this phrase, elementary as written. And if a reaction is elementary, or elementary as written, it tells you that you can say that A, the stoichiometric coefficient in your balanced chemical reaction, is equivalent to alpha, and B is equivalent to beta. But this is only the case when you're told this. It needs to be very explicit. You need to be explicitly told this. Otherwise, you know nothing, because we cannot tell you anything about the kinetics, the reaction rate. We cannot tell you anything about the reaction rate based on stoichiometry alone. You need someone to go into a lab and empirically determine how fast your reaction occurs based on the change in concentration of one of your reactants. And just to kind of expand on this a little bit, sometimes, for first order reactions, having species B might not matter, and in that case, beta or B, little b, can be equal to 0. And the only thing that would really matter would be the concentration of A. So this generic equation does apply to a significant number of chemical reactions. And to explicitly define what is the reaction order, which is typically denoted with the variable n, is equivalent to alpha plus beta. And so if our coefficients were both 1 and this was an elementary reaction, we would have a reaction order of 1 plus 1, which would be 2, so this would be a second order reaction, for instance. And if we were to now perform a dimensional analysis and look at our reaction rate constant K, or K sub A, this definition of reaction order becomes a lot more important, because performing a dimensional analysis on K is a function of n, the reaction order. And so what I mean by that is, if we have a 0th order reaction, which means that this reaction, which is pretty rare, but it does not care about either concentration of A or B, In that case, what we would find would be Ra would be equal to K, and therefore K would need to have units of moles of A, or moles of anything, per volume per time. Now, what happens if it's a first order reaction in which alpha is equal to 1 and beta is equal to 0, for instance, would be minus Ra is equal to K times Ca to the first power. What we would find is that K would have to have dimensions of 1 over second. If we were to look at a second order reaction, just so that we can begin to see the pattern here, what we would have is minus Ra would be equal to, and I'm going to truncate B here and just say KCa squared for simplicity. What we're going to find is that K will have dimensions of 1 over second times, and then essentially inverse molarity squared, or inverse molarity, which would be equivalent to cubic meters per mole. Sorry. And what you're going to find here is that as this pattern increases, as we go out to third order, sorry for my bad handwriting, but you will see that this term would then become squared and cubed and to the fourth. And so doing your dimensional analysis on your reaction rate constant becomes more important with higher order reactions. In addition to that, there is an example that I want people to take home, which is non-elementary reactions. So huge caveat here is non-elementary reactions. An example of this would be the following, which we have CH3CHO decomposing into methane, and carbon monoxide. And in this reaction, just to write it out more explicitly, we'd have 1 mole of CH3CHO becoming methane plus CO. Someone who mistakenly believes this is a first order reaction in their reaction rate equation, or their rate law, would come to an incorrect assumption, because the kineticist would tell you that actually the rate of consumption of CH3CHO is really equal to K times concentration CH3CHO quantity raised to the 3/2 power. And so this really highlights an example in which we cannot strictly rely on stoichiometry. Even though this is 1 right here, this disagrees with this, so you cannot always assume that your reactions are elementary as written. So that is going to wrap things up for this video. I hope it helps. Let me know if you have any questions, and thank you guys for watching.